Okay, in the previous chapters, we already know what's the function or how to use the binary phase diagram, and we can find the eutactic and the eutactile reactions in your phase diagram, right? Okay, so today we're going to look at the most metals or the alloys that we are going to use in our industry is the carbon and the iron alloy, or say it's a steel. Okay, it's a steel. Okay, so what's the function of carbon atoms? What's the function of carbon atoms in iron matrix? It's like what's this function of the carbon atoms? It's like a disperse phase, right? Disperse phase, right? And what's the property of this disperse phase? It's hard and brittle, right? And what's the function? It's the to strengthen its mechanical strength, right? So this disperse phase can enhance the mechanical property of this alloy or metal. Okay, and for the certain composition of carbon atoms in iron matrix, and when we heat up at certain temperature range, uh, the alloy is called the austenite foam. I will introduce you what is more detailed about this austenite, but currently you just remember this. Okay, austenite or gamma solid solution in iron and carbon phase diagram. Okay, and when we cooling down at a specific temperature and the composition, this austenite will transfer to two solids. Okay, one is called the cementite, and the other is called the ferrite. That is alpha solid solution. So we already knew this from the previous chapter that one solid transfers into what? Two solid, right? Two solid solution. And this reaction is what? Eutactile reaction, right? Eutactile reaction. Okay, therefore, in this chapter, those issues to address are the transformation, how the mechanism that transfer one phase into another, and how long it's going to take, and how does the rate of the transformation depends on time and temperature, right? And it is possible to slow down the transformations so that non-equilibrium structures are found. And are the mechanical property of the non-equilibrium structures more desirable than equilibrium ones? Okay, so we're going to discuss more about this transformation and the kinetics during a phase transformation. Okay, and the behavior of metals and alloys depend on their composition, structure, processing history, such as the heat treatment. Okay, and improves the mechanical property by heat treatment, which modify microstructure. Therefore, what is the most important parameters to modify metal or alloys microstructure? The heat treatment, right? Just heat it, just heat treat. Okay, so let's look at the process of alloy. Okay, so initially we have the pure metal, right? Okay, for our case, it's like iron, and the alloying element be added. For this case, it's carbon atoms to form the alloy. Therefore, from those experiments, we can, for example, we can plot this phase diagram, right? And we can observe this microstructure from the microscope. Okay, and we can tell what the solid solution is and what its point defect type is, and whether the intermetallics form or not. Okay, and this alloy can be divided by two categories. One is ferrous, and the other is non-ferrous. Okay, ferrous and non-ferrous. Ferrous, cast iron, or ferrous like stainless steel. Okay, the difference is its composition. Okay, it is a composition. For the iron carbon system, the cast iron, whose carbon content is from 2.6 to 6.67 weight%. From the non-ferrous stainless steel, the carbon content is less than 2 weight%, with the very high concentration of chromium content. Okay, and how to strengthen it, or how to modify the microstructure to strengthen their mechanical property are different. Okay, for the non-ferrous cast iron, can just like trench, right? Can trench, annealing, okay, and tempering or normalizing to modify its microstructure. But for the ferrous, non-ferrous stainless steels, okay, use a solid solution to enhance its mechanical property, and the precipitate and the hardening and aging process to modify its mechanical strengths. Okay, so simple diffusion-dependent transformations in which there is no change in either the number or composition of the phase present. This concludes solidification of a pure metal, allotropic transformations and recrystallizations and grain growth. Okay, therefore the self-diffusion dependent transformation, no change in either number of composition of the either the number nor the composition of the phase present. Okay, we have to remember that. And there's some alterations in phase compositions and often in the number of phases present. But finally, the microstructure ordinarily consists of two phases. Okay, for the phasal transformation, finally, a microstructure has two different phases. Okay, and the third type of transformation, phase transformation, is dimensionless, wherein a metastable phase is produced, such as the martensitic transformation. That means the cooling rate is extremely fast, that diffusion cannot occur. Okay, therefore this structure is almost amorphous, because the crystal doesn't have time for diffusion. Okay, the kinetics of the phase transformation. Most solid state transformation do not occur instantaneously, right? Because the obstacles impeded the course of the reaction and made it depend on time, right? So no matter what kind of the reaction, okay, the phase transformations always need time to complete. Always need time to complete. Of course, for this diffusionless, for the martensitic transformation, well, maybe time is not independent. Time is independent, because with this cooling rate is very fast, extremely fast. Okay, I will introduce this later. And since some transformations involve the formation of at least one new phase, some atomic rearrangements via diffusion are required. Therefore, we already know the Fick's law and Fick's second law, right? The Fick's second law is time dependent. Okay, it's time dependent. It's a transit state. will consider a transit state for phase transformation, because the phase transformations always need time, Okay? And the formation of a new phase is the increase in energy associated with the phase boundary that are created between the parent and the product phases. Okay. Okay, so two stages involved in the formation of particles of a new phase are nucleation and growth. So the nucleation process involves in the formation of small particles of the new phase, which are stable and are capable of growing, or we can say it's this particle, or we can say it's seed or island. Okay, seeds or islands. Okay, and the the structure will grow from those particles. That's new particles or new phases. Okay, and the growth stage is simply the increase in size of new phase particle. Okay, the new growth stage is just increase the size of this particle or islands or seeds. Okay. Therefore, the nucleations, the seeds acts as a template or islands on which crystal grows. For nucleus to form, rate of addition of atoms to nucleus must be faster than rate of loss. And once the nucleated grows, proceeds till the equilibrium is attained. Okay, so that's the process of a nucleation. And the driving force to nucleate increases as we increase the delta T. Okay, the delta T represents the supercooling or superheating. Okay, I'll introduce what is supercooling, superheating later. And for small supercooling, that means slow nucleation rate or slow cooling rate. So if we cool alloy very slowly, what's going to happen? That a few nuclei forms with large crystals, and if we cool alloys very quickly, so what's going to happen? That many nucleates form and small crystals with small crystals. Okay, that's close to amorphous. Therefore, we can look at this picture. This shows the seed, right? Seed, or we say it's nuclei. Okay, and this nuclei will keep growing, right? Will keep growing. Will keep growing like this. It'll keep growing, keep growing, keep growing. Okay, and when this nuclei keep growing to form the gram size, to form the gram boundary, right? Therefore, for this nuclei keep growing, we see the gram boundary form. Right, we already mentioned what is the gram boundary is, and it's consisting of the nucleus, right? Okay. Okay. Therefore, if the cooling rate, the supercooling rate is extremely slow, so what's going to happen? That means this seed is few. Okay, is few. For example, if let's give you some examples. Okay, so if the cooling rate is very slow, that means the C layer is few, right? Therefore, the gram boundaries are few. Okay, For example, for the slow cooling rate, okay, let's draw another picture here. Okay, for slow cooling rate, the C layer is only few of them. Therefore, finally, the grand boundary, because the crystal will grow on this C layer, right? It will keep growing, and this will keep growing, right? By diffusion. Therefore, finally, there are only few grand boundary film like this. Okay, like this. Okay, if this cooling rate is fast, so we have higher number of nucleoside, right? And each nucleoside start to grow, and finally we're going to form higher number of grand boundary, right? Therefore, like this. Okay, so you know what I'm saying? That's what is saying here. For the slow nucleation rate or cooling rate, few nucleus. For the rapid rate, many nucleus. Okay, few slow rate with the large crystal, and the rapid rate with small crystals. Okay, therefore, this crystal is larger than this one. Okay, so this is the slow, and this is the fast. Okay, so we can compare the difference between fast and the slow cooling rate corresponding to its growth of crystals. Okay. Okay, so the superheating and supercooling corresponding respectively to heat or cooling above or below a phase transition temperature without, remember this, without the occurrence of transformation. Okay. And this phenomena occur because right at the phase transformation temperature, the driving force is not efficient to cause the transformation occur. The driving force is enhanced during superheating or supercooling. Okay, so why we need the superheating or supercooling? Because we cannot remember we mentioned this phase diagram called a TIM-LAT binary phase diagram, and this transformation temperature is about 183, right? If we want to melt this alloy, this TIM-LAT solder or TIM-LAT metal, if we just heat up at 185, do you think it's enough driving force to melt this alloy? Of course not. Therefore, we need superheated here. That means we heat up above the phase transition temperature. If this temperature difference is larger, that means the driving force is higher. Okay, the driving force is higher. Okay, the same thing if the cooling, the supercooling is below the phase transition temperature. Okay, so if we cool this TIM-LAT alloy at the eutectic reaction, that means the temperature has to below 183, right? If this temperature is reached 180, so do you think this structure is equivalent or not? Right? If we can cool it down to say like the 100 Celsius, below the 183, that means we have the higher driving force to facilitate or to enhance this phase transformation process. Okay. Okay, so let's look at the nucleation types, homogeneous nucleations, that the nuclei from the bulk of the liquid metals requires considerable supercooling 80 to 300 Celsius. Okay, so the homogeneous nucleation, that means the nucleus form in the bulk of liquid metal. Okay, in this case, this temperature or supercooled temperature has to below 80 to 300 Celsius, below the this phase transition temperature. For example, if we have the if we have the eutectic reaction such like this, right? I think you already know it. Okay. Okay, and this temperature is the phase transition temperature, right? If we choose the specific composition at this point, okay, and we're cooling down from this temperature to this temperature, or we from the temperature 1 to temperature 3, it's 2. Okay, so tell me, what's the driving force for the phase transformation? I mean, if we just cool the temperature to the 0.2, and whose transformation process, or whose transformation, the driving force for transformation is low or high compared those processes if we cool into the 0.3. Therefore, we cite the delta T from 1 to 2. It's right here, right? Delta T, 1 and 2. And if we find the delta T is from 1 to 3, T, 1, 3. So which one has the higher energy or higher driving force for phase transformation from liquid to solid, if this is a eutectic reaction? Of course, from 0.1 to 0.3, right? Because the delta T is larger than delta T1, 2, right? Okay, and the second type is the heterogeneous nucleations. So what's the heter means? That means the different type, right? The different type. And the homo means the same. Okay, the heter means the difference. So the heterogeneous nucleations is much easier, since the stable nucleus, since that the stable nucleating surface is already present. Okay, such as the moldwood or the impurity in the liquid phase. So what's that mean? That means the different phases or the different seed already existed in this liquid metal. It could be from the impurity, maybe there's some this impurities from your process, right? From your process, or this impurity from the moldwood. Okay, so the two different type of the nucleus. Okay, and this kind of nucleation just need a very slightly supercool. That means the delta T, right, is small. The delta T, we don't need the higher driving force to form this heterogeneous nucleation. Okay, and this kind of nucleation of a precipitate occur mostly on the surface, already present, as I mentioned, already presented in the structure, like the grain boundaries or the defect. Okay, defect. Okay. And so let's look at the rate of the phase transformation. We have to consider now the kinetics. That's a study of reaction rates of phase transformation. Okay, so how to determine the rate, the reaction rate? We have to do the experiment to measure the degree of transformation as a function of time. Okay, so there's different measurement approaches to determine the degree of transformation, like X-ray diffraction or the electroconductivity measurements on a single specimen, and measure the propagation of thought waves on a single specimen. So here, I just want to let you know, we can run the experiment to define its to define or to measure the degree of transformation as a function of time via the experiment. Okay. Of course, we're not gonna discuss more detail about those experiments. However, we have to realize that, okay, we can measure it. We can run the experiment to know its degree of transformation as a function of time. Okay, let's look at the results. Okay, so after we run the experiment, we can define the degree of transformation, right? And we can plot this figure. It's the fraction transformation versus time on log scale. Okay. Okay. So when the time reached to the 50% of the fraction transformation, the phase transformation, we define it. When this phase transformation reach the 50% to here, right? This point, right? To this point. And we can figure out how long it's gonna to reach the 50% of phase transformation, right? So we define it like a t.5. Okay, t.5. So by those experiments, we figure out an equation they call the Arami rate equation, like this. And why is the fraction transform no matter what kind of the this reaction? Okay, no matter what kind of reaction. Okay, so y defined as the fraction transform. Okay, and the k and n fit for specific sample. That's the constant. Depends on your reaction. Okay, your reaction. Okay, and we define the rate of transformation is the reciprocal of the time with 50% transformation. Okay, so we define the transformation like this. This is transformation rate. Okay, so first we can find this curve from experiment, right? We can find this curve from this experiment, this curve, right? This curve. Okay, we can do numerous experiments. And after that, we fit this curve to define the equations called the Arami rate equation. Okay, and we find the time for 50% of fraction transformed. Okay, and we took the inverse of the time of the 50% of the 50% of the fraction transform. We got the transformation rate. Okay, we got a transformation rate. Okay, so initially there's incubation time for nucleation. Okay. Okay. Okay, so let's look at this figure. This reaction is called the recrystallization. Recrystallization at different temperature. At different temperature. So for copper, recrystallization of copper with different temperature. So what's this figure tells us? What's this figure tell us? Rate increases with increasing temperature, right? So what is the rate? We already mentioned in the previous slide, the 50% of phase transformation, right? Is so the time of the 50% of phase transformation, right? And we took the reciprocal of the T.5. Okay, so we define it as a T.5. That means the 50% of the phase transformation. Okay, and we took the inverse of it, so we got the transformation rate. And rate often so slow that attainment of equilibrium states are not possible. Rates are often slow. Okay, that's for sure. It's very slow. Okay. So let's look at this figure. So after we find out this rate, right? It's a reciprocal of the time of the 50% of phase transformation, right? And we can plot the relation between temperature and rate. Okay. Temperature and rate. And for this green dot line means the, when for this blue dot line right here, the blue dot line here is the nucleation rate. We just count the number of nucleation site formed. Okay, and for this green dot line is the growth rate. Okay, the growth rate, and we can combine it. We can combine it to a total rate of transformation. Okay, to find the total rate of the transformation. Okay, so what's this figure tells us? Temperature and the rate. So from this total rate of transformation, we can find out the there is the maximum transformation rate with us at the specific temperature, right? And below the equilibrium transformation temperature, or the phase transition temperature. Okay, so we can define this temperature as TE, equilibrium. For the Team Lab soda, the temperature is about what? For the Team Lab soda, the temperature is about 183, right? Right. Okay, so if we need we need a fast rate of transformation, right? We can find out the specific temperature. Okay, from this figure. Right. Therefore, we know, okay, so if we need a the faster rate of transformation, what's the delta T? What's the supercooled temperature we needed? Right, so we know the supercooled temperature is in this range, right? From the TE, from the TE to this point, right? That's a delta T. Right? Therefore, we know, okay, cooling down to the specific temperature to reach the maximum transformation rate. Okay, so we have to figure out the nose. It's called the nose. Okay, and then you can find out the time. Okay, how long it's gonna take to reach the fastest transformation rate? Right? We have to know the time. Right? From the TE, the equilibrium transformation temperature, supercool to the specific temperature, and how long it's gonna reach the maximum transformation, the rate of the maximum transformation. Right? So we can find the minimum time. We can find the minimum time here. Okay, and the maximum transformation rate right here. Okay. Okay, so think of the other way. That is, if we heat up this alloy to reach the TE slowly, right? Or heat up or follow the from this specific temperature and heat up to reach this TE very slowly. And this curve will not reach this equilibrium transformation temperature. It will just as close it as possible. Okay, and the time probably, if we really want to reach the equilibrium state, the time maybe needs very longer. Okay, it's very longer. Okay, maybe infinity. Okay, because the cooling rate or the heating rate is not possible very slow. Okay, it's not possible very extremely slow. Okay, it's not possible. Okay, it's not possible. Okay, so let's look at the figure here. Let's look at the effect of the temperature on recrystallization of cold work copper. That's a copper. Okay, it's the copper. Okay, it's the copper. Okay, it's the copper. Okay, so just recrystallize it. I will introduce what the recrystallization is. We just recrystallize this copper at different temperature. Right, so first we can figure out, okay, the transformation rate depends on the temperature, right? Increase with temperature increase. So for the temperature at 135 has the highest transformation rate, right? Compare with others. Okay, compare with others. Okay. And let's look at the example that is the some from our textbook that determine the activation energy for the recrystallization of copper from the sigmoid, the curves in the figure below, like this, that I already show you in the previous slides. Okay, if we fit this curve, we can find out it's kind of an exponential function. So do you guys remember the Arrhenius equation? Okay, right? So we can define this curve as the growth rate equals to constant times exponential function, Q over RT minus Q over RT. What is the Q? Q is the activation energy to trigger this reaction, this recrystallized reaction occur. Okay, okay. The temperature effect is the supercool or undercooled temperature that dominates this growth rate or transformation rate. Okay, so from this figure, what we can get. Okay, so let's show you this figure as represents some process, manufacturing process. corresponding to its mechanical property. Of course, with respect to the temperature. Okay. So think of this situation. If we have the a metal or alloy which has been strength hardening with very high hardness. So how to modify its mechanical property? How to modify its mechanical property? By heat treatment, right? In the very beginning, I already mentioned that heat treatment is the crucial parameters to control the microstructure of metal and alloys. Of course, it's highly correlated to their mechanical properties, right? So if a metal alloy already being strength hardening, that there must be residual stress existed, okay, with very high strength and high hardness. Okay, so how to modify its mechanical properties? By heat treatment, right? By heat treatment. Therefore, at certain temperature, below certain temperature, we have to recover this the grain being strength hardening, right? It depends on the materials, depends on the metal. Different metals have different recovery temperature and different crystallization temperature. Okay, therefore, if we just heat up at the recovery temperature, its residual stress begins to reduce. Okay, initially, its residual stress reduced, and the strength hardness will quietly remain. However, its ductility slightly increase. Okay, slightly increase. Okay, when we keep heating up to reach its recrystallization temperature, that's mean the new grams form, right? The new gram. Okay, the new gram form. So what's the use of this new gram? Well, the mechanical property of those new gram must be lower than that of the old grams, right? Therefore, the mechanical property will reduce substantially, and the strength and hardness will substantially decrease, and the ductility increase dramatically. Okay, because some new grand foam. And if we keep raise the temperature, that the grain will start to grow. The grain will start to grow. Okay, at this stage, this hardness will reach those mechanical properties will reach stable, like hardness and strength will reach stable, and the ductility will reach stable, and those residual stresses are diminished, disappear. Okay, and then we can plug a table to represent this figure, right? So this table represent this figure. Okay, so we know, okay, we just as this recrystallization temperature here, right? And we know it's what? That's time for 50% of fracture of recrystallization, right? Therefore, this is the time 0.5. Okay, time 0.5. Okay, and then we take the reciprocals. We get or this rate of phase transformation, or the rate of the recrystallization. Okay, and then we can plug this table into a figure. right? And we already know, okay, we can take the log, the rate transformations follows Arrhenius equation. So a plot of this, the growth rate, the natural log of growth rate versus temperature, the inverse of temperature, right? Allows us to calculate the constant in the equation. And we can take in the natural log of both sides of the equation. We get this, right? We can convert the exponential function into a linear function. Okay. But that we can take the log of this size equals to what? Log A, right? Minus Q or T, right? Like this one. Okay, we just take the log of both sides here and here, right? And we can get the linear equation. Okay, and we can plug this into a linear function. Okay, and we find the slope. We find the slope of R over Q, right? Minus R over Q, right? And then we can calculate the activation energy, right? We can calculate the activation energy, and you can find out the constant A. Okay, you can find out the constant A here. Okay, so this the linear function is like this. Okay. Therefore, it can be a references for industry or company that's okay. Say we are gonna heat treat the process of recrystallization of copper. Oh, I know this curve, this linear relation can be used as the references, right? Therefore, we can say, okay, so what's the temperature? Usually we'll have the temperature for the Celsius on the top, but doesn't matter. So we can have, okay, this is a specific temperature. We gather this growth rate and the specific growth rate. Okay, so this figure will help the company or industry for their processing. Okay, for their processing. Okay, and I will finish this for after we finish this figure. So in the beginning, I mentioned the eutectoid reaction, or in the previous chapter, right? You guys already know what's the definition of eutectoid reaction or transformation. That's mean a phase, a solid phase, convert into two solid phase, right? Right. Okay. So this phase diagram shows the iron and the carbon phase diagram. And there's a specific composition. There's a specific composition of carbon to form an intermetallic compound. So what's that composition in this phase diagram? Okay, representing intermetallic compound. What's the composition of carbon? Okay, what's the composition of carbon? Well, it's about 6.7, right? Do you remember that we mentioned there are two different types of intermetallic compound. One is stoichiometric, right? And the other one is non-stoichiometric, right? So what's this type is in this phase diagram? Of course, it is the stoichiometric intermetallic compound because it's the straight line, right? It's a straight line at a specific composition of 6.7. Okay, and what's the composition is for this eutectoid reaction or eutectic transformation? Which composition is? I think you can find it. Okay, it's about like 0.76 weight percent of carbon content, right? Because you can look at this composition right here. Okay, the transformation is from one solid to two solid, right? Two solid. Okay, so where is the reaction? Where is the eutectic reaction? So what is the eutectic reaction? What's the eutectic reaction? What's the definition of eutectic? Eutectic means from single liquid transfer into what? Two solid, right? Two solid, right? Transfer into two solid. So which composition in this phase diagram represents eutectic reaction? Or can you draw a vertical line on this phase diagram? Okay, so where's the reaction of this liquid transferred into two solid? Here, right? Can you find out that at this composition? Right? One liquid transferred into two solid phase. Okay, two solid phase. And the transformation or the equilibrium temperature of the eutectic reaction is 1148 Celsius, and the temperature and the equilibrium temperature for the eutectoid reaction is about 727 Celsius, right? Therefore, for the eutectic reaction, the temperature must cool to below the 727 Celsius. Okay, and for the eutectic reaction, for the eutectic reaction occur, the temperature must cool below the 1148 Celsius. Okay, okay, so today's course we're gonna end it here, and you guys have to fully realize the phase diagram of iron and the cementite or the carbon. Okay, because that's the materials, the metals or alloys that most widely be used for all those industries. Okay. Okay, so see you next time.